Wednesday, where we looked at this curve right here, y equals 2 to the x. And we said this is called exponential growth because the base was more than 1. If the base is more than 1, it's exponential growth. Here in example 2, we're looking now at an example where the base is less than 1. So this is not going to be exponential growth. All right. Let's put together a few values on our table here. And I'll just call on some folks. You just give me a random number to plug in. Don't pick anything crazy because I don't want to make that many tick marks. All right. Jackson, we'll start with you. What number would I need to plug in here to get a good start? All right. So let's plug in the number 2. So that means that we're going to have 1/2 to the second, which is 1/4. So when x is 2, y is going to be 1/4, or just above that x-axis. Okay, William Bryan, pick me another value. All right, so if I pick x equals 3, there we are. If I pick x equals 3, it'll be 1/2 cubed, which is 1/8. Okay, which is even lower, closer to the x-axis, right down there. Okay, Drake.
Would it change if you swapped the zero?
Oh yeah, that would change the whole game. That would be it'd be a square root function or a cube root function or whatever. Ashton.
-2.
-2. Okay, beautiful. -2. Now, if I got 1/2 to the negative second power, that's going to be 2 to the positive second power, or 4. Remember, raising a fraction to a negative means flip the fraction, make the exponent positive, and when we flip 1/2, it becomes 2/1, or just 2, and then 2 squared equals 4. So when x is -2, 1, 2, 3, 4, I got 4 tick marks right up there. Maybe a couple more values. Jacob, let's plug in 0. Okay, so 1/2 to the 0 equals what, class? 1. Good. Anything other than 0 raised to the 0 equals 1. So we plug in 0, we get 1. That's my y-intercept. And let's put one more value on here. Let's do we'll do 2 values. We'll do 1 and we'll do -1, just for dexterity's sake. Here. And of course, I didn't get all of it. There we go. There we go. We'll plug in 1. We get 1/2 to the first power, which is 1/2. And we get -1, which is 1/2 to the negative first power, which is just a simple 2. So we got 1/2 here. Gosh dog it. OneNote, quit jacking me up here. I don't know about you guys, but like when I write, do y'all ever, when you write, you brace your pencil with like your pinky on the paper? Like, or when you might put your palm down here like that. You know, so like if you do that on the screen, I'm preaching to the choir here. But anyway, if you do that to the screen, it like moves the screen around, which is a bit annoying. But anyway, I deal with it. So like if I play connect the dots now, I mentioned this is not exponential growth, is it? Does anybody know what this is called? So close. Say it louder, Quinn. Exponential D. Luke, that would have been a terrible thing to say. Thank you for not saying that. If you go to the dentist because your teeth are not very good, you might have tooth. You might have tooth decay. You might have tooth decay. Yes, this is exponential decavity. No, this is called exponential decay. Exponential decay. All right. Bless you. Decay. And exponential decay occurs when the base is between 0 and 1. Write that down. You'll see it in a slide here a little bit later on. But exponential decay occurs when the base is between 0 and 1. Exponential growth occurs when the base is more than 1. If the base equals 1, it's just a boring flat line, horizontal line. And so there you go. Notice what we did. We made an X and Y table. We plotted several points. We connected the dots. Now we kind of have a good understanding of what both exponential growth and exponential decay should look like. One of the things that both of these curvatures have in common is that they both have an asymptote. An asymptote being an imaginary sort of boundary line. In this case, both of these curvatures are asymptotic to the x-axis. Drake. Okay, so like 1/2 to the 1/2 power would be the square root of 1/2, which would just be some irrational number. Square root of 2 is 0.707 would be what that's approximately equal to. Right. Which by the way would fit in with our picture right here, right where my finger's at. It's about 0.7. Right. Jacob.
What would tell you that you have a function with exponential decay?
All right, so beautiful. That's a very important question. If you didn't hear what Jacob said, I'm going to reiterate it. He said, what would tell you that your function is an exponential decay function? So I'm going to answer that a couple ways. Number one, it is a constant base raised to a variable exponent. That's why this is very different than like those quadratic functions that you guys have been studying. Y equals 2 to the x is very different than y equals x to the 2. All right, do we recognize the difference there? This one right here is quadratic. We're used to dealing with it. That's a power function. Very comfortable with it. An exponential function is where you have a constant value, a constant number raised to a variable. So that right there helps me identify, oh, this is an exponential function. Now, what tells me if it is growth or decay is what kind of base there is. Hold on, I scrolled down too far. OneNote is having some issues today. So what tells me if it's exponential growth or exponential decay is the base. If the base is more than 1, it's growth. Okay, it's taking off. If the base is between 0 and 1, it is decay, is declining, it's decay. If the base equals 1, then it is a straight, horizontal, flat, boring line. Okay. We don't deal with the base of 0, again, because that would be trivial. It'd be a horizontal line at the x-axis with a hole in the middle. And if the base is negative, the graph jumps all over the place, and it's a discrete graph, and that's, again, not germane to this discussion. So you got two types of exponential functions, growth and decay. And you can tell the difference between the two right there. Will?
Could the graph either start or end at 0?
We'll get into that in an example here in a minute, but no. Exponential growth and exponential decay functions have a domain of all real numbers. Because, think about it, no matter what my base is, okay, I can always raise my base, whether it's between 0 and 1 or whether it's more than 1. I can pick a number, and you can always raise that number to a power. Whether it's a big positive power or a big negative power, you can raise it to a power. So the domain is going to be all real numbers. And that means that it's reaching infinitely to the left and infinitely to the right. And it just depends on what you want to plug in to get there. Luke.
So is your base like the base y equals 1/2? Is that your base? What is your base?
All right, so let's go back to our examples. We'll talk about Java in a second. Java the dog, not the drink. All right, so like in this example right here, example 1, our base was 2. The base is what you are raising to a power, okay? So in this example, the base was 2. In our second example, the one that we've been looking at today, Luke, what is the base? Very good. So the base is what's sort of, like when you were learning handwriting, how you would say, well, this is where your letter goes, and then like my kids learn it, like if you have a G with a little tail, the tail goes down to the basement, right? And so like what is on the line right there, it's not a superscript, it's not a subscript, it's a normal number, and that's what our base is. All right, so if the base is negative, what I was going to say is that's kind of what we refer to as a discrete graph. It bounces around all over the place. I swear I do not know what our system is doing that is lagging so hard. Somebody must be Using some bandwidth today for some reason or another. I'll pull up a picture of what that would look like for you, Drake. All right. So like you don't have to write this down. Just you can kind of listen to the explanation. The question was, what happens if I have a negative base? All right. Well, look, remember what happens with negative numbers raised to even exponents? What's a negative number raised to an even exponent? Wrong, wrong.
Oh, it's I.
Pick a negative number in your head, and I want you to square it. What is it now? It is now positive. A negative number squared is positive. What? You didn't daggum say positive.
No, I meant to
Yeah,
say
he
positive. I
did.
said even.
You said even. You said something other than positive.
I did say I said positive first. I'm not both wrong, and then I was like, oh,
All right. Maybe I misheard you, Luke. I can admit if I make a mistake. But anyway, hey. So, what about a negative number raised to an odd exponent? It stays negative. So we got a problem here because with exponential growth, you know, everything is positive and it's go, go, go. With exponential decay, again, everything is positive and it's decline, decline, decline. With this one, it's jumping around. It can't make up its mind. It's going negative, positive, negative, positive, negative, positive, negative, positive. And then look at the one in red right here. It's an in-between value. Like raising something to the 1/2 power is the same thing as taking the square root of that something. So how would I, with a negative base, how could I raise a -2 to a 1/2 power? It would be an imaginary number. It wouldn't show up on my graph. So this is what's called a discrete graph, where you just got a bunch of rando dots plotted in a particular pattern, and there is no continuity. I couldn't connect all those dots. So a negative base is out. We don't consider it part of this exponential growth or exponential decay discussion. You know, real good question, Drake. So what I want to look at now, okay, we've looked at an example of graphing out a basic growth curve. We've looked at an example now of graphing out a basic decay curve. Both of those have an asymptote, asymptote. You and I have talked about asymptotes before. This picture is of a dog named Java. All right, Java is no longer alive. Java was a dog my wife and I adopted. There's a cute little picture of her right there. We adopted her. We'd probably been married a couple of years, so this was back in 2009, I guess. And we adopted Java, and she was a good dog. We took her camping with us. You know, she was a house dog, and just a good little pooch. She was a mix between a dachshund and a corgi. And so anywho, Java had this friend, let's say, named Roscoe the Basset Hound. Okay, Roscoe lived 3 doors down the street, and Roscoe loved to come into my yard and take a dump. All right, and Basset Hounds can take some big old dumps. Let me go ahead and tell you that. I don't know if anybody in here has a Basset Hound, but if you do, you know what I'm talking about. So Roscoe, I was always getting frustrated with. So was Java. Java did not like Roscoe coming in her yard and pooping. The problem was we didn't have a fence. I didn't want to build a fence. And so my wife and I got what's called a collar system. Okay, it's not an invisible fence. They didn't come out and bury cables or anything. What we did is we got like a bucket that sat in our kitchen, and it emitted a radius. Have I already told y'all this? Y'all are looking like I've told you this before. It emitted like a frequency within a particular radius, and you could dial the radius up and make it real big, or you could dial it down small and make it real small. And Java would wear a collar, and if that collar got outside of the radius, it would go beep, 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 and then it would emit a shock, and there was like 8 levels of shock intensity. Java was a coward, so we always left it on 0, so it wasn't a shock, but it was just a beep, 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 and she knew, oh crap, I'm about to get shocked. I need to get back in the yard, because I think we let her get shocked once just to teach her. So anywho, the collar system worked in such a way that I didn't have to have a fence. It was great. Dogs stayed in the backyard. And she knew where that curve was. She knew where that radius, that boundary line was. And she would get as close as she could to it because Roscoe would come by the yard and you know, try and tease her or whatever. And she'd get real close, but she wouldn't cross it. She wouldn't go past that boundary line. That's sort of like what an asymptote is, okay? You look at I've still got some of the curve up here from the previous example. Look at that blue curve. It is getting closer and closer and closer to that red dotted line, isn't it? That's like the invisible fence. That's like the collar system. That curve is Java. That red line is the fence, and she's just getting closer and closer and closer to her boundary, okay? So when a function behaves asymptotically, that is what it is doing. It is getting closer and closer to its asymptote, to that imaginary line, let's say, okay? So when we consider, I got a new example for you here. When we consider the exponential function that I've got up here, y equals 3 to the x minus 2 plus 1, one of the first jobs that I have is to determine where the asymptote is located. Where is my boundary line located? And I'll go ahead and let the cat out of the bag, so to speak. This value right here is going to inform us as to the location of our horizontal asymptote for this exponential function. Go ahead and write this example down. There's a lot on the screen, so you can be writing. One of the things that you need to also notice is that this right here is a general form for the exponential function. General form, what do I mean by that? If you can look on my blackboard right here, I got y equals ax squared plus bx plus c. We've seen that all year long. That's the general form of what kind of function? You just said that because Alperin said it. Y'all are both wrong.
Standard. Oh, that's standard.
Y equals ax squared plus bx plus c. That's a quadratic function. It's a standard form of quadratic function. But there are other forms. Here, since you can't see it, I'll write it up on the screen. There are other forms of a quadratic function like y equals a quantity x minus h squared plus k. We call that the vertex form of a quadratic function. My point is that sometimes we learn about a function by learning about its general form. In other words, what it typically looks like, the template, if you will. And then we learn about, ooh, what are these parameters? What does that h and k do? What does that a value do? Or up here in this case, you know, my four parameters are a, b, h, and k. Okay? And each of those parameters affects the curve in one way or another. So first of all, let's identify what our parameters are. Here's my problem. Here's my example down here. It's y equals 3 to the x minus 2, and then plus 1. So I want to identify my parameters. What do you think a is for this example? Nobody in my 8th grade class got that this morning either. There's a 1 understood out in front, right there. Okay, so a is 1. B, my base would be what, Hogan? What's my base in this example? Good. Okay. Now, h is the number that we're subtracting from x. So what am I subtracting from x in this example? 2. And k is what we're adding afterwards. So k is 1. So identifying the parameters is a good exercise to begin with. Okay. So we identify the parameters a, b, h, and k. And let's talk a little bit about what each one of those can do. This is where you're going to be taking some notes because I'm not going to write this down, but we're discussing. We're having a talk. All right. So first of all, a, the way in which a affects my curve is just like with the field goal versus swamp patrol kind of discussion with quadratics, right? If a is positive, we've talked about before how the quadratic curve, the parabola is concave up. If a is negative, it's concave down, okay? Similarly, if a is positive here, then my curve, I don't want to say concave up, although that's, I guess, technically what we can say. The curve is going up, okay, in either direction. Here if it's growth, here if it's decay. If a is negative, it's going to do what? It's going to flip it. Very good. It's going to flip it down. I like my little black chair example, right? You guys remember the black chair? If I multiply by negative out front, what does it do? It flips the chair upside down. Okay? So A has to do with the orientation of your curve. That's perhaps what I would jot down if you haven't already written that down. A affects the orientation of your curve. Okay. B we've already discussed. If B is greater than 1, it's growth. If B is between 0 and 1, it's decay. Sebastian, Santiago.
Why would you take the negative 2?
It is whatever is being subtracted from x. So x minus h, x minus 2, therefore h is 2. Another way of looking at it is I've used the phrase before, bass-ackwards. On the inside, it's the opposite of what you would think it is. Actually, let's get to that now. Let's talk about h. What do you think h will do to my parent function? Very good, Quinn. Say that again. It'll move it or shift it left or right. In class, what do we think k will therefore do? Shift it up or down. Excellent, excellent. You guys remember about our little transformation. I want to show you another picture. See if I can find it. Where's this at? Where's this at? Here it is, here it is, here it is. Perfect. I knew I wrote that down earlier. All right, this is a summary of what we've talked before about regarding shifts, right? So like a plus on the inside of a function is going to be counterintuitive, bass-ackwards. When you think a plus would shift to the right, it actually shifts it to the left. A minus on the inside shifts it to the right. Okay? A plus on the outside shifts things up. A minus on the outside shifts things down. That is the way that you would think that it is. So again, I would write those 4 things down. You know, don't make me hold your hands as far as note-taking. If you see something good on the screen, write it. Now, with these kinds of transformations in mind, back at this example 3 right here, what do you think a minus 2 would do to my parent curve, my normal growth curve? A minus 2 is going to shift it 2 to the right. And a plus 1 is going to shift everything up 1. So my horizontal asymptote, instead of being at the x-axis, is now going to go up 1, and it's going to be a dotted line right there at y equals 1. Yes, William?
Is it bass-ackwards if it's connected to the thing? If it's connected to B?
What do you mean by that?
If it's like 3 to the, or 3 to the x, like when do you know it's bass-ackwards?
When it's being done, any operator that's being done to the argument of the function. And what I mean by that is like what your function is actually doing. If it's the square root function, your radicand is your argument. If it is like the quadratic function, what you're squaring is the argument. In this case, the exponential function, the exponent is the argument. So in other words, I call it like the inside of the function. So that's what we would say is the counterintuitive part where, ooh, if I see a minus 2, that's going to shift it to the right. Anything that's being done on the outside, in other words, that is sort of like an afterthought. Okay, so like here's the meat and potatoes of this function, and we just got a little plus 1 tacked on at the end. The one that's, quote, tacked on at the end is where it is the way that you would think it would be, and that's going to be your vertical effect. Did I answer your question? Okay. All right, so everybody cool on how we got our asymptote shifted up 1 unit, okay, because of that plus 1. Now, I would normally have a y-intercept at 0, 1, but what we've said is we're going to shift 2 units to the right and 1 unit up, and so that point now has been mapped to a different location, okay? By the way, we could always make an x and y chart to get some of these points, right? I could just as easily say, well, what happens when x equals 3? Okay, plug in 3. You tell me what you get out. Think. 3 minus 2 is 1. 1 being the exponent. 3 to the first power is 3. 3 plus 1 is 4. So 1, 2, 3, 4. Very good. Okay, maybe what happens if I plug in 0? Okay, 0 minus 2 is -2. 3 to the -2 is 1/9. 1/9 plus 1 is just a little bit higher than 1, right? So I already can tell this curve is behaving in that manner, okay? So we got it sketched out. We're talking about the y-intercept, the asymptote, the domain, the range. We'll talk about domain and range in just a sec. Got it right.
You can plug any number, right?
Correct. And actually, that speaks to my next question. What is my domain? What's the set of allowable inputs here?
Everything above.
Very good. If we're using interval notation, that's how we'd write it. Here, domain, we say all real numbers. Range, we say y has got to be greater than 1. Not equal to, right? Because I could get them in my car and drive a mile down the road, and this curve is getting closer and closer and closer and closer and closer to that asymptote, but it's never going to actually get there. It's getting infinitely closer to that y value of 1. Okay? This is what is referred to as exponential growth, just maybe with a little bit of a shift because of some parameters there. Will?
So if it was like plus 2, it would be close to like 2 mark.
Yeah. So like if it was plus 2, it would look like that. And in essence, what plus 2 would mean was that each of these points would just be 1 unit higher. Can y'all visually see that? That like if I wanted to, from Perron's question, if I wanted to say, well, between the green and the red one, let's add another. You're just shifting every point consequently up 1 unit, okay? So like whatever point it is, way down to the left, way over to the right, it still gets shifted up just 1 unit. Good question, Will. Kreitz, you had a hand up. William Bryan. Yeah, that's a great question. Let me look into, I'm gonna call a couple of exponential function questions from the ACT next week. I'll let you guys practice. That's a good point to bring up there, William. Typically they would, obviously they're not going to say, please graph the following exponential. They don't do that on the ACT. But they might say, okay, they might say, yeah, they wouldn't ask it that way. They would be more inclined to like give you like some of these kinds of word problems that we're going to be working through, right? That can be modeled by an exponential curve. Okay. All right. So our next point of discussion has to do with money, and you guys very likely have seen something similar to this in the 8th grade. You probably saw something called simple interest. Simple interest, comparatively speaking, is just that. It is simple. Simple interest just means, hey, I borrow some money from you. You charge me a particular interest rate. I give you your money back plus a little extra. That's simple interest. This is what is referred to as compound interest. Okay? Now, I know there's a lot of stuff on the screen right there, so buckle up. Now, in blue is what is called our compound interest formula. Write the blue formula down. It is called the compound interest formula because what money, okay, so like let's say I borrowed some money from Cash, okay, the appropriately named banker, Cash. And I say, Cash, I want to borrow some money from you, dude. And he says, all right, I will charge you. No, you know what? Let's not do it that way. I'm not going to borrow money from Cash. I'm going to invest money with Cash. I'm going to say, Cash, I'm going to give you some money. I'm going to invest in your business. All right. And so, like, let's say I start off with a small, modest investment of $100, and I give him $100. That's what's referred to as my, quote, principal investment. P, in other words. P is how much money goes in initially. So I say, Cash, here you go. Here's $100. Now, Cash is in, some kind of business where he's making a pretty good rate of return. Rate of return, or rate, a ratio, a percentage. That's what R stands for. Okay? So if Cash says, Coach Morgan, I will make you 6% on your investment. That's the rate of return. Or that's the interest rate, if you will.
Wait, what is A?
I haven't got there yet. But to read it, it says amount. I know my handwriting sucks. I'm sorry, guys. Amount of money in the account after T years. That's what A stands for. All right. So anyway, we talked about principal investment. That's how much money I gave Cash to begin with. He had said, Coach Morgan, I'll pay you 6% interest, or your investment will earn a 6% rate of return. That's what R stands for. Okay. Now, Cash is going to compute the earnings not just once a year, but Cash is a businessman. He's going to compute it once a month. So the number of times that he computes that interest, so he says, here, Coach Morgan, here's how much money you've earned, is called the number of times that it is compounded. And the number of compounding periods per unit of time is N. Okay, so like let's say I go to the investment firm of Cash, and I say, Cash, how often will you compound my investment? Will you compound my interest? He might say monthly, so N would be what? Thank you. N would be 12. There are 12 months in the year. Okay, so if it's daily, N would be 365. Good. Unless it were a leap year to be 366. Correct. Compounding periods per year. Number of compounding periods per year. All right, so that's very good. That's what we're talking about. It's the number of compounding periods per year. All right, now T would be how long am I leaving that money invested with Cash? How long am I leaving my money in that account? That's what T stands for. That's the duration of the investment. Like, let's say I'm investing with Cash so that my kids can go to college, right? And Teddy is about to turn 10. He'll go to college when he's 19. So I've got like 9 years, let's say, okay? He's got a June birthday, and so he's younger. Well, I guess so. That would be he'd be going to college when he's younger. Then you're right. So T would be 17. It'd be 9 years then.
Wait, so
Because he's 9 right now, and in 9 years he'll be 18. I said he's about to be 10.
listen close.
Hey, dadgum, it doesn't matter, fellas. We're getting good grief. We're getting bogged down in semantics. T is the duration of the investment. Okay. So like it's how long do I want to leave the money invested? And then A is the amount, like let's say I come back to Cash after that number of years. I say, hey, Cash, I need my investment now to pay for college. And he gives it to me. That's the A. That's how much money is in the account after all of this has transpired. So A, T, P, R, and N, these are all of our parameters, if you will. We'll get there in just a second. We're talking about the blue one right now. Talk about the blue one. All right, so Cash, in his investment scheme, he invests and it pays me interest, what did we say, monthly, right? So 12 times a year. So what that means is that Cash, what was your interest rate, Cash? It was 6. Ashton's listening, Cash. This example's about Cash, and daggum Ashton's listening. Maybe I'm going to go to the investment firm of Ashton. Salami Ahud Incorporated. All right, anyway, I'm just messing with you, Cash. So your monthly compounding, but that doesn't mean that I get a whopping 6% every month. That's not what that means. That means that he takes his 6% that he's quoted me, which is a yearly rate, and he cuts it up into 12 parts. And so I earn a 12th, or in this case, a 0.5% each month. Now, when I invest my initial principal investment with Cash, and after that first month goes by, he is going to pay me a 0.5% of my initial investment. Now, class, my initial investment in this little example was $100. What is 0.5% of $100?
50 cents.
50 cents. Thank you. 50 cents. Okay. Nick Pace, are you with me, son? All right. So now my account doesn't have $100 in it anymore. How much does it have in it? $100.50. So listen to me, man. This is key. For the second month, he's going to pay me that monthly 0.5%, not on $100 anymore, but on $100.50. And so my first month of interest is now helping me earn more interest. So that's like a snowball. That is the power of compound interest. I can't remember who said it. It might have been Albert Einstein. But he said the most powerful force in the universe is compound interest. Okay? The idea is that it grows how? Use an E word. It grows exponentially. Because what parameter I control is, of course, P and T. Okay? Cash is going to control the N. Cash is going to control the R. I control how long it's in, and I control how much money I put in to begin with. Okay? Now, okay, go ahead, Kreitz.
So what is compounding period exactly?
In this case, it would be a month. Like in our little example, N is how many compounding periods there are in a given time period in a given year. So N would be 12 in my little example with cash.
So if it was a month and it was like a certain month, it'd be like 30 or something. 30 days.
So like if I invested for a month and they said we'd be willing to pay a compound every day, then depending on the month, that N value might be 30. Typically what we'll see though is we'll see compounding periods per year. That's the vast majority of the examples we'll encounter. All right, so compound interest works based on a year. You're giving me a yearly rate, and then you're going to chop it up into a certain number of parts. Will Perone.
Would you make more interest yearly or monthly?
So that's the great question. If all things are equal, and let's say I go to Cash and I go to Ashton, and Cash says, Coach Morgan, I will compound your interest monthly, and Ashton says, Coach Morgan, I will compound your interest quarterly. Quarterly meaning every 3 months or 4 times a year. N would be 4. I'm going to Cash all the way. The more compounding periods, the better. Because although Ashton's taken that 6% interest rate and each, he's cutting it up into fourths, which would be like 1.5%, I'm not getting that compounding effect as often. And so the more compounding periods would be advantageous. Let's say I go over here to Hogan, and Hogan's like, well, screw that, Coach Morgan. Heck, I'll compound every day. I'm going to Hogan now. The more compounding, the better.
So it all depends on the person, or like what situation.
Correct. And you as a savvy shopper need to shop around because what 2 things does the bank control or the investment firm control? They control R and N. Okay? How much they're willing to pay. So Ashton might say, you know what, Coach Morgan, I'm not going to compound every month, but I'll pay you 6.1%. Hogan might say, I'm going to compound every day, hey, but I'll only pay you 5.5%. And as a savvy shopper, I need to do what? I needed to compare and see which one is better suited. Hey, look, we'll pick up with this. Is a compound interest. This compound interest stuff can be complicated. We'll pick up with more of it on Monday. Okay. In the meantime, be rocking and rolling on that Delta math. Live Jesus in our hearts. All right. And I appreciate you guys. Thank you so much. See you, Wilson.
What did you do? Like second month. Yeah.